Energy distribution. Here we have a simple circuit where a cell transfers energy to a lamp. In a circuit like this, that's normally all we really consider. But the connecting wires will also have some resistance. This will cause them to heat up, taking some of the energy that will not therefore be supplied to the lamp. The lower the resistance of the wires, the greater the proportion of energy supplied gets to where we want it, in this case the lamp. Now in a circuit like this, using copper wires, the resistance is not normally a problem, but the lengths of wire needed to transfer electricity around the country make these energy losses significant. Silver has a very low resistivity of just 1.6 times 10 to the minus 8 ohm meters, but silver is clearly far too expensive to use for overhead power cables. Copper is not far behind with a resistivity of 1.7 times 10 to the minus 8 ohm meters, but it's still quite an expensive metal, and it has a high density, which means that the power cables would be quite heavy and need a lot of support, and copper is also a very ductile metal, which means it stretches easily. Aluminium has a low density, meaning lighter cables, and a low resistivity of 2.7 times 10 to the minus 8 ohm meters, but aluminium on its own is not strong enough, and so generally a steel reinforcement is used as well. So the overhead power cables have a structure something like this, with an aluminium outer of several cores and a steel inner for strength. As an example, we could find the resistance of a 10 km length of aluminium power cable of radius 1 cm. For this we need the equation R equals rho L over A, where R is resistance in ohms, rho resistivity in ohm meters, L the length in meters, and A the cross-sectional area in square meters. The resistivity of aluminium was given earlier at 2.7 times 10 to the minus 8 ohm meters. 10 kilometers is 10 times 10 to the 3 meters, and our area is pi times the radius of 0.01 meters squared, giving a resistance of this length of wire of 0.86 ohms. But when looking at the efficiencies of distributing electrical energy around the country, resistance isn't the only factor we need to consider. To improve efficiency, there is another consideration as well as the resistance of the wire. In resistors, the heating is caused by collisions between the electrons and the positive ions, leading to increased vibrations. The greater the current, the greater the number of collisions, and therefore the greater the heating effect. Now, electrical power is equal to current squared multiplied by resistance, and so a doubling of the current will lead to 4 times the energy losses through heating. But as power is also equal to current multiplied by potential difference, we can transmit the same power using a low current and a high potential difference. This is easier to see using a simple example. We want to transfer 24 watts of power across wires which have 2 ohms of resistance. Now, in the first case, we can have a potential difference of 12 volts, a current of 2 amps, and the wire's resistance is 2 ohms. From power is equal to current multiplied by potential difference, this is a current of 2 amps multiplied by a potential difference of 12 volts, giving our required power of 24 watts. But this 2 amp current through the wires, using power is equal to current squared multiplied by resistance, gives a heating power in the wires of 8 watts. So we're losing 1/3 of our power in heating the wires, rather than sending it to where we want it. If we increase the potential difference 8 times to 96 volts, we then need a current of just 0.25 amps, a quarter of the current, the wires still have a resistance of 2 ohms. Now, power is equal to current multiplied by potential difference. 0.25 times 96 still gives us 24 watts of power. Now for the heating in the wires. Power is equal to current squared multiplied by resistance, which gives a heating of the wires now of just 0.125 watts. Much better than the 8 watts we were losing with the higher current. Mains electricity is alternating current, or AC. This means it changes direction. In fact, the mains changes its direction on a cycle of 50 Hz, or 50 cycles per second. This is opposed to batteries which supply direct current, or DC. This always goes in the same direction, from the positive terminal round to the negative terminal. It's easy to alter the current and potential difference of alternating current using a transformer. However, transformers will not work with DC. We find that as power is equal to current multiplied by potential difference, as the current goes up, the potential difference goes down. In fact, if the system is 100% efficient, if we double the current, we would halve the potential difference, and so on. Now, the transformer consists of an iron core and a primary coil of wires and a secondary coil of wires. We apply an alternating current to the primary coil and we get an alternating current out. For this transformer, the secondary coil has more turns than the primary coil, and this then is a step-up transformer. The potential difference is increased and the current is reduced. This transformer has more turns on the primary coil than the secondary coil, so this is a step-down transformer, and in this case potential difference is reduced as current is increased. Transformers can have an efficiency of over 97%, so it's quite easy to fit them into an energy distribution system. I'm going to build up a diagram now showing what happens between the power station and the end user. Well, a power station produces electricity at around about 25,000 volts. Quite a high voltage, but not high enough. It's immediately sent through a step-up transformer, which will send the electricity out at either 275,000 or even 400,000 volts. This is for the long-distance journey around the country. This is known as the supergrid. As the power lines enter a built-up area, they would pass through a step-down transformer, reducing the potential difference to around about 132,000 volts. As they got closer to built-up areas, another step-down transformer would reduce to 33,000 volts. At this potential difference, heavy industry may take a direct supply, but this will be too much for most users. Another step-down transformer would have an output at around 11,000 volts, which would suit some light industries. But it would also need to pass through another step-down transformer before it could be sent at 230 volts to domestic customers. These final step-down transformers are very close to the end user, and near your home you've probably seen a small building about the size of a garage, fenced off with danger signs. That will be your final step-down transformer. If there are a very small number of homes, sometimes the transformer will be about the size of a fridge and mounted on the top of a telegraph pole.